So thank you very much, Tom, and all the other organizers. Right, so this will be, I'll try to make this as light as possible, and it won't be a full hour talk. So. And as you can see, all of this is joint work with Mariana Hargus, and in fact it's work in progress. Okay, so let me begin by showing you what I mean by a generalized solitary wave. So, I mean, a solitary wave, as you all know, is a traveling wave which decays to zero at spatial infinity by a generalized solitary wave, or they're sometimes called solitary waves with ripples. I mean, something which converges to a periodic wave train at infinity. And so, well, it won't matter that much in this talk, but there might be a phase shift between these two different wave trains. So plus and minus infinity.
Finite amplitude at infinity.
Yeah, that's important. It's not oscillations which decay to zero. There's actually finite amplitude. Okay, and so that's one thing which was in the title, generalized solitary waves, and the other thing was instability, transverse instability. So I mean, what we're interested in basically is to see if, well, so I mean. We all know that the KdV soliton is supposed to be very stable. The question is, can there be some kind of instabilities coming from these ripples at infinity? So you can all guess the answer.
Well, isn't there an issue between a central spectrum?
Yeah. So, I mean, we have to make it a bit more precise. So examples of where such generalized solitary waves appear are, for example, water waves. I mean, that's the main motivation for me, at least. So if you have small bond number, I mean, bond number between, so water waves with surface tension, I should say, and gravity. So, I mean, it's when you have this dispersion relation of the form where it goes like this. So you have waves which are slightly supercritical here. I mean, there is a resonance with periodic waves with non-zero wave number. So then there are simpler equations like the fifth order KdV or Kawahara equation. So I'll refer to it as the Kawahara equation in this talk. Other examples are coupled KdV equations and internal waterways, for example. Okay, and yeah, so as I've already mentioned, for the waterwave problem, you can formally derive the KdV equation, of course, as a model for any value of the bond number, but it's just that you have this resonance for beta between 0 and the third. Okay. And this pretty much summarizes what I already said. So we know that the KdV soliton is stable to 1D perturbations as well. If you look at the soliton as a solution of the KdV equation, and it's also stable to transverse perturbations if you embed it in the Kp equation. So, well, with the correct one, the one with small surface tension. And if you look at the zero surface tension case, then, well, they also have some kind of stability properties. I mean, there's this paper by Pego and Sun. So we are interested in these ripples and whether they can destabilize the waves. Okay, so, and for the most part of this talk, I'll concentrate on the Kawahara equation just to keep things simple. I'll say a couple of things about the water wave problem at the very end. And so this is the 1D model, one spatial dimension. And to study transverse instability, we also need a 2D model. So this will be the fifth order Kp equation. And so both of these can be derived rigorously as model equations for water waves if you look at this particular parameter regime. So you take a bond number close to 1/3, and to get those signs of the coefficients, the bond number should be slightly less than 1/3. And then you do this with scale. Okay. So then first let me talk a bit about traveling waves for the Kawahara equation. So we need to look at both periodic waves and then these generalized solitary waves. So this is, well, the dispersion relation you get if you linearize around the zero state, the Kawahara equation. And you can see that it's similar to the picture below, where you have this sort of minimum at a non-zero wave number. So again, you can anticipate there that that you will get some kind of generalized solitary waves by looking at well, solutions with slightly positive wave speed. Okay. So to capture those generalized solitary waves, we also need to look at the periodic waves, which bifurcate, sort of close to here with this wave number. Well, you can do that in different ways, but one way you can do it, which is similar for the water wave problem, is to write that as a spatial dynamic system. So you just make a traveling wave ansatz, and then you get a fourth order ODE. You just integrate once in space. And it's reversible, and then what you get is a well-known bifurcation in dynamical systems, where you have, well, so when the speed is 0, you have double eigenvalue at 0, and then you have a pair of purely imaginary eigenvalues. And as you increase the wave speed a little bit, so you go up this dispersion curve, then these 0 eigenvalues will move off the well, away from 0 and they're real. Okay, and there's a lot of theory about this kind of bifurcations in the literature. So what you obtain, first of all, is that there is a 2-parameter family of periodic traveling wave solutions, even. And so they're parameterized by, I'm using the amplitude A and the speed C as the 2 parameters. Okay, and it's a little bit special here, so you can't really do this just by, you have to rescale the solution as you can see here. So as you can see, the main part has A times C in front of it. So if you just let C go to 0, then this whole thing will actually vanish. So it's not really, you have to do something special. You can't just sort of fix the wave number, the wavelength, just bifurcate. Okay, so these are the periodic solutions, and then we want to study the generalized orbital waves, so sort of homoclinic connections between these periodic solutions. Heteroclinic. There's this phase shift at least. There's been a lot of theory on this, whether you can find solitary waves, true solitary waves, or generalized solitary waves in the last 2 decades, 3 decades maybe even. There will be some history, I think it's on the next slide. So at least what is known is that you can find generalized solitary waves, and you can make the amplitude of these ripples at infinity very small, but not necessarily 0. So you can in fact even make it exponentially small in the parameter C. So the theorem which I stated here is a little bit complicated to understand, but just shift that. So phi is the periodic solution, and as you can see here, this is the phase shift, and then H is the solitary part, so clinic part. And yeah, so this is so this is the amplitude. You can make this amplitude of phi in that regime. So you can see that the minimum of the interval of amplitudes is exponentially small in the square root of c. Okay, so these are the ways you want to study are phi of A and C, and this u of A and C. Okay, so here is an incomplete history of the problem. And I should say I've concentrated here on the fifth order KdV or Kawahara equation and the water wave problem with a free surface. There's also work for internal waves, for example, by Grimshaw. So I mean, there were numerical computations done in the 80s, and then I think the first by Jean-Marc Hunter. Then I think the first rigorous result for Kawahara was by Hunter and Shirley in 88. And then there were a lot of improvements on this. So for the water wave problem, I think the first rigorous result were by Biel and Sö in 91. And then, well, so for this exponentially small amplitudes, this is pretty difficult and quite technical. So there was first some formal asymptotics, and then I think the first rigorous result for the water wave problem was by Sun and Shen, and then the person who was really the expert on this is Erik Wahlén, who's written this very thick monograph on the problem. And as you can see at the end here, there's been some discussion on whether you can actually get the amplitude to be 0. And so at least there is some result that if you're close to bond number 1/3, then you can't actually set it equal to 0 by assuming Sun. And then there's numerical indications or strong numerical indications that for a wider range of bond numbers, it's also not possible. I'm sorry if I missed anyone else on this list. Okay, so now let's turn to the stability analysis and get back to the problem you mentioned. So, well, what we're looking at here, I should say, is a linear stability analysis.
You've switched equations too, haven't you?
Yeah, so this is for the fifth order KP equation.
I have also a question. So is that the dt dx of the first term, or is it a typo?
No, that should be dt dx.
But in the one-dimensional you have the dt, yes?
Yes, but I have an extra derivative in the right hand side. So it's like what you do in KP. You can, okay, if you want, you can put this dx as a dx inverse. So that's also, Mariana also always calls this equation the sixth order KP equation, because 6 extra, if you write it like this, you have 6 x derivatives on the right hand side, but I think in the literature it's usually called the fifth order KP equation. Yeah, so I'll mention, I'll get back to the water wave problem at the very end, but for now I'll stick with this. Okay, so, well, we're interested in a linear stability analysis, so we linearize around a solution. So far U star is just a solution. Yeah, I should say also maybe I've written it in a moving frame as well. I don't know if I had it in a moving frame before. Okay, so U star is, it could be the periodic wave or it could be the generalized solitary wave. But anyway, U star is supposed to be independent of the transverse variable y. So to start this, we can just take the Fourier transform in y, and then instead of having, then the y variable will just be result in a parameter omega squared. Okay, so A star is now the operator which we're interested in studying, and so I mean, to study stability, you normally look for well, if you want to find prove instability, you want to find some kind of going mode solutions, so an exponential in time. So if we make this ansatz, then that's the equation that we get.
Is it V, the last equation?
Sorry?
The last equation should be
Oh
V.
yeah, it should be V. Sorry. Okay. So we make this answers and then we change U to V.
Actually, it's also true for you.
Yep. Okay. Okay, so now to Tom's remark. So I mean, we have to. I'm going to be very sort of loose here and just define the solution to be spectrally transversely unstable if this operator is not invertible in some Hilbert space to be specified. Okay, and of course, if you want to prove any kind of nonlinear instability result, then you're going to need some more information than this. Okay, so if, of course, if minus omega squared is actually an eigenvalue of that operator, then you do have linear transverse instability. So you have an actual Roggen mode solution. And otherwise, so this is essential for a talk, or for my talk, if minus omega squared is only in the essential spectrum, then we say that U star is essentially transversely unstable. And then that probably is not going to be good enough to do anything, a nonlinear analysis with. You're probably going to have to know more about the solution. Okay. So what we're then able to prove is that these periodic waves, well, which you find the ripples at the infinity, are actually linearly transversely unstable with respect to coperiodic perturbation. So in other words, we work in space of periodic functions with the same period as these waves.
Remind me now, with regular KP, is that not true? Periodic solutions.
So you have to.
Regular, these would be the conoidal waves.
Right. No.
Are they transversely stable in KP2?
In KP2.
Has that been done rigorously?
I'm not sure. Is that it might be included in what Mariana's done recently?
For small amplitude.
Small amplitude, yeah.
What is the result? Are they stable? Just wondering if this is a surprise or not, that they're unstable.
Yeah,
This is a surprise to me.
I'm not sure.
Okay.
Has Mariana done dimension breaking for periodic waves in KP, which would
Yes,
probably
that's-
imply the linear
Yes,
transverse
so I think there are,
instability of them?
Even in KP2?
Even in KP2?
Third order or whatever.
KP2 is the for
The small surface
small
tension?
surface tension.
Yeah.
Yeah. No, I think it's KP1, isn't it?
Yeah, KP1 we know where they would be unstable, right? Or we would expect them to be unstable. But KP2, okay, well, anyway.
I'm not
it's
sure about
surprising.
KP2. Yeah. Okay, so that's the first result. And then the second result is, okay, so these are just, I mean, when you want to talk about the generalized solitary waves, then first of all, we should study localized perturbations, or at least perturbations with allow different periods. So the second result says that both of these periodic waves and the generalized solitary waves are essentially transversely unstable with respect to these localized perturbations. Okay, and that result essentially follows from theorem 1. So
Okay,
it's just that your background state is unstable.
Yeah.
So that,
So you say nothing about the existence of eigenvalues?
no.
So the first term is sort of superharmonic instability, or
Yeah.
the business is some period.
It's the same here. Okay, and I should say here that, so you may ask me, why are we looking at transverse instability? Well, I mean, the first question to ask is, what about 1D perturbation? So this has already been done by Hergus, Lombardi, and Shield. So they looked at these periodic solutions and proved that they're actually stable to 1D perturbations, both co-periodic and localized. And we, as you will see in the next slide, we rely on their results. Okay, so I'm just going to sketch this proof. So it's basically pretty simple. There's no real advanced math going on here. We just look at this linearized operator and then we rescale it so that so Z is a rescaled horizontal variable just to make it 2 pi periodic. Okay, and so we call this new operator B. And so we can solve this in a space with a fixed period, 0 to 2 pi. Okay, so then the point is that, okay, so what we do is essentially expand this in powers of A. We keep C fixed but small. And if you do that, then if you look at A equal to 0, you just get the constant coefficients operator. So you can just use Fourier series and see that the kernel is 3-dimensional and the rest of the spectrum is negative. It's bounded away from 0. So all you have to do is essentially study these 3 small eigenvalues. See what happens when you turn on A. And a lot of the work has already been done by Argus, Lombardi, and Shield. So they actually studied, well, they didn't study exactly this operator. If you take away one dz in front of it, then that's the operator that they studied. And they proved that for that operator, there is you have 2, 0 eigenvalues. So the kernel is 2-dimensional when A and C are small. So then we automatically get that there are 2 elements in the kernel, and then there's a third eigenvalue which we have to study. So we just have to show, well, to prove instability, we just have to show that that eigenvalue becomes positive for small a. So, and that's just a simple perturbation analysis, more or less. You just expand in the powers of A and compute a little bit, and this is what you find. So this coefficient, so the leading order is like C squared times A squared times some positive coefficient. So that means that if A and C are both sufficiently small, then there is a small positive eigenvalue. Okay, so then minus A star has a unique simple negative eigenvalue. Okay, and so that was sort of the spatial part. Now I have to add the temporal part. And again, that's just a sort of a perturbation argument. So I know that without this lambda dx, there is a simple eigenvalue in the left half plane. So then if I turn this lambda arm, then, okay, so it's going to move around a little bit, but yeah, I mean, you're still going to still have some simple eigenvalue in the left half plane, and in fact, it has to be real because the operator is real. So we have symmetry with respect to the real axis, and there's only one. And this is going to be lambda, which is your minus omega squared. Okay. So this was instability with respect to coperiodic perturbations, and then for these periodic waves, then instability with respect to localized perturbations is follows sort of directly from Fouquet block decomposition. And it's sort of trivial in this case because you have it for coperiodic perturbations. So I mean, you can just decompose your spectrum as I mean, you just had to study the spectra of these sort of shifted operators instead. And then from gamma equals 0, you know that there is one. So.
Question?
Yeah.
You know if the 1 for gamma equals 0 is the largest growth rate, or?
That I don't know. so that was for the periodic waves, and then we also have to look at the generalized solitary waves. So that's done by, sort of standard argument where you compare with these with limiting operators as x goes to plus or minus infinity. And so I mean, it's sort of these limiting operators will now be exactly, since the generalized solitary converges to these periodic waves at plus or minus infinity, what you're going to get is exactly the spectral problem for the periodic waves. And then you also, so you have compact perturbation of these operators. And so you know that the essential spectrum is preserved. Okay, so that concludes the second theorem. Now in the remaining minutes, so this really won't be a full hour talk, let me talk a little bit about the full water wave problem. So the goal is to study.
Can I ask a question about the previous part? What do we expect to see in a situation like this? Because it's the tail that's unstable, not the wave.
Yeah, that's a good question.
So it's conceivable that it might be okay.
Yeah, it might be. You might not see. Might be.
Depends on which direction the tails are going in, when they go unstable, and that kind of thing. You know? So you haven't looked at any of that.
No, we haven't. It would be interesting. I don't know if you can do any kind of numerics on this. Interesting to see. Okay, so for the water wave problem, so I'm considering I haven't even written down the equations. It's the standard Euler equations, potential flow, and so the gravity capillary problem in this Kawahara regime. So the idea is to use, if you heard Mark Groth's talk, then the idea is very similar. We write this problem as sort of spatial dynamics formulation. So we're, instead of considering the evolution in time, we consider the evolution in a transverse variable, which is now z instead of y. I guess I should have changed that. And t is just sort of considered as a parameter in the problem. And so you can write it in this very innocent form, but then these functions have sort of suppressed the difficulties here in these functions f. So they look like this. So this is the difficulty. So this wretched thing, expand it in the correct way. But as long as you have some patience, I should say also here there's an additional complication because you have this nonlinear boundary condition, free surface. So you have to make it first. You have to make a change of variables to linearize this. Okay, but so then the basic idea is to look at the linearized problem again. So we start with a periodic solution, and so you have to prove that this has a pair of simple purely imaginary eigenvalues by reducing to a perturbation of the Kawahara equation. And then,
are you near bond number of a third?
Yes. Okay, so in the Kawahara regime, in 1/3. Okay, and then there is a trick. So you have to show that this is preserved if you add basically the temporal part. So here you consider the growth, the exponent in the exponential as a small parameter. And you can here use reversibility to prove preserved. Okay, and then the idea is to use similar arguments as above to consider generalized solitary waves. So all you're going to get is some kind of essential transverse instability. Okay, so some things which would be interesting is to investigate. So this was for the Kawahara regime where the bond number is close to 1/3, and it would of course be interesting to look at the full range between 0 and 1/3. And yeah, nonlinear instability would be interesting, but there's a big gap because we have very little information.
What's the extra difficulty in going away from 1/3? It's related to Tom's question whether the KP2 periodic waves are transversely stable.
Yeah.
I mean, if you knew that, then you could do the same kind of perturbation argument as here.
That's what you have to do. But so I think there's still probably going to be, maybe even in some cases, there might be unstable to 1D perturbations. But no, it's just we started in this corner, and then I hope we can expand. But yeah, you won't have the Kawahara equation. So. So this is the last slide.
Oh, okay. Well, thank you very much. Plenty of time for questions. If anybody has any.
I mean, the obvious question to ask when you prove a linear or any kind of instability, and it's linear, is actually what happens to the solution. I mean, where does it go?
Yeah.
You're saying that solution, you try and integrate it numerically or whatever.
Yeah. So
It doesn't persist, so what happens? And the interesting thing here is you're studying the generalized solitary wave as a steady solution. Of course, that doesn't actually exist physically because it requires energy sources at infinity things. What does happen is if you take a localized initial condition to the Kawahara equation, you generate a one-sided generalized solitary wave, which is actually losing energy because it's radiating out to the ripples. So the question you might be able to answer is this. The one-sided one is decaying because it's sending energy out to the ripples, but you're implying that it's actually also maybe unstable in the transverse direction, and therefore growing. So which one wins? Right.
Have there been numerical experiments just to put the generalized solitary waves in a time-dependent code? Yeah.
In the KP version of Kawahara.
Yeah.
okay, you done experiments?
No.
Oh, okay.
No.
No, I mean numerical. Okay.
Why is there this concern about infinite energy? Because to say that infinity is a Stokes wave, and we don't talk about Stokes waves as having infinite energy.
No.
But now we do when it has a little localized bit in the middle.
That's right. I know.
So
that's
a bit of a contradiction there.
Yeah, I was thinking about that too.
Yeah, so explain.
Well, it gives the ripples on both sides, so they cannot satisfy the radiation condition on both sides.
Oh, okay, that's a different argument. That's about his
That's
argument
right,
about
that's
radiation.
And that's why you
Yeah.
need it on one side.
Yeah. So by that same argument, Stokes waves can't exist either.
For an infinite train, yeah.
For the periodic waves, this would give the existence of, I mean, we get some dimension breaking here as well. Using this one.
Okay. Okay, well, then let's thank all of our speakers. Oh, sorry.
Well,
Go for it. We got time.
All the way at the beginning, when you talked about the scaling that led to actually to the KP setup, just it went by a little bit fast. Right there. I was surprised to see an epsilon cubed on the y, because usually for KP you'd have epsilon on x and then epsilon squared on y. Yeah.
Epsilon cube is the question.
It
Right.
might be specially for KP or fifth order. That might be a different scaling required for fifth order.
But that shouldn't affect y. That should affect.
But it's right if you look at the term.
That's right.
equation.
That's right.
You've got 6x derivatives and 2y derivatives. And it's got one the cube of the other.
So y.
Oh. Except something fourth and y. That's a.
Right. So usually when you go from KV to KP, you assume this weak two-dimensionality.
Yeah.
And then that's why you put the epsilon squared on y. So why would you put epsilon cubed on y? There's a lot of y's in that sentence.
You would have put an epsilon.
It does seem to make sense, because if you add up all the epsilons, like
Yeah, no, I agree.
epsilon
But,
fourth,
I agree, but why wouldn't you put epsilon squared on y?
the equation wouldn't be in balance at that point. Then the
No,
line
you've got a
term.
different equation.
Your beta is 1/3 minus epsilon squared. There's another epsilon squared coming in a different place here.
No, it's because the normal dispersive term in KdV has gone to 0.
Exactly.
Because of the coefficient there.
Yeah,
So it's rescaled to make it higher order in Y.
Yeah.
it is kind of interesting.
The coefficient would be 0, but now it's epsilon squared.
A great audience, you answered.
Good, was that clarified then? I'm done. Okay, well, let's thank all of our speakers today.